Okay, a warm welcome again to everybody that's participating in our live webinar today. Let me know, I think our voiceover is pretty good today. So let's get started on the subject matter. And today we will go through a webinar in regards to mold steel selection. Before we do that, let's just talk a little bit about what's important in injection molding. Cause and effect behaviors in injection molding. This is a very important subject matter that we have taken on in our online learning tools with Kruse training, as well as in these seminars and these webinars, excuse me. So what's important is cause and effect behavior in injection molding. We will talk a little bit about the Circle of Knowledge training program and then we go right into the mold design, mold steel selection lesson. We'll go through this lesson to discuss a little bit the importance of mold steel selection for the mold designers. And then we have a little Q&A. So if you have a question, just use the chat function and try to type in the question for me. If I will see it in time, we'll go through it. And of course, you're always welcome to send me an email. At the end of this presentation, you will have the opportunity to see the contact information, but I'm sure you have it. You know, you signed up, so you know where I am if you want to find me. Let's see here. Let's go on. Okay, so understanding complex behaviors and interactions in the molding industry is critical in order to stay competitive and ready for the future. That is definitely true. As we all know, injection molding is a complex manufacturing process. And if you understand the interactive behavior in injection molding, what I mean with that is when you design a part, you really need to optimize the design in combination with the plastic. Yeah, so a design for a polycarbonate part will be different than for a polypropylene part or for a PEEK part or a nylon part. It's going to be definitely different. So each molded part has certain requirements. So we need to figure out what these requirements are. There are, for example, critical dimensional tolerances we need to make sure we know about. Then there are structural strength requirements we need to address with the part design. Most often we have appearance and aesthetics, you know, class A surfaces on visual parts in especially automotive and medical devices, just to name a few. So those are important to know as well. And then, of course, acceptable shrinkages and warpage behavior. How does a part shrink? What type of added shrink we need to put into a tool to make sure the part comes out correctly after molding. And of course, most parts are assembled. So the assembly functionality is important to know. If you just think about valve covers in the underhood applications automotive, a valve cover gets always mounted to an engine. You know, what are the requirements in regards to the, hole distances, the vibration, et cetera, which goes back to the structural strength, of course. So there are many things we need to take into consideration when we design a molded part. that goes into the mold design, and the processor needs to be aware of this as well, because he really at the machine has to have the knowledge of what's important for these part designs, the requirements, to make logical decisions on the process itself. Of course, the molder has the least amount of impact when it comes to creating a high quality part. A high quality part starts with the design. Okay, so with our training program, this is really our mantra, is really trying to train and give knowledge to part designers, mold designers, and processors, so they can understand each other a little bit better, what their business really is. That's very important, because if the part designer will never be a molder, for sure not, and a molder is probably never going to be a good part designer. But if they can talk to each other intelligently and help each other out, what's important in their respective businesses, then the time to market and will be much shorter. The quality of the part will definitely be increased if those fashions, part design, mold design, processing, talk to each other. So that's why we created what we call the Circle of Knowledge. We have online lessons available that really teach the concept of the circle of knowledge, the interactive behavior. They all are about 15, 20 minutes long, very focused learning, as we call this. And that's what we will be doing now, is we will look at a lesson from this learning tool called Mold Steel Selection. So let me show you how to get to this lesson. I'll navigate through the website here quickly and show you how to get to these lessons. So when you have a login, and you're fortunate enough to have a login, then we really can go to our lesson plan, and let's focus on the lesson for the mold steel selection. Currently, as you can tell, we have a bunch of lessons already. We have about 96 now. And let's go to the mold steel selection lesson. We will click on Start, and let's get moving.
Injection molds are designed and built to allow parts to be produced from various polymers and to be utilized for a variety of applications. A mold design team must possess the ability to evaluate and determine the optimal mold steel for each mold component to effectively produce high-quality plastic parts. In this lesson, you will learn the most common mold steel materials and what attributes they should possess, the best mold steel options for different polymer materials, injection pressures, and production cycles, temperature distribution behavior for molds with different mold steels and mold components. Generally, mold steels can be divided into ferrous and non-ferrous groups. Ferrous metal contain iron, while non-ferrous materials do not. The most common mold steels are shown on screen and include some grades of aluminum and copper alloys.
Of course, there are many more, as we know, but these are really just the common steels, and mainly used in the industry currently are basically H13. There's a lot of stainless steel. Sometimes you see S7, even D2, but P20 is the steel of choice for most of the applications for mold bases, etc. And then for core cavity, H13 if they need to be resistant for wear resistant, and usually 420 is stainless steel for corrosion applications, and it's basically used for a lot of things, stainless steel.
A mold designer needs to decide which material and steel hardness to use for both mold plates and core cavity components. Mold steel for injection molds should have the following attributes. It should be economical, have quick and easy machinability, have the ability to be through hardened, allow for the application of surface treatment, have high fracture and crack resistance, have temperature shock and wear resistance, and have a high thermal conductivity.
Man, this is a long list. But the mold makers usually have a stable of mold steels that they are used to machine and use for injection molds. So, but basically, this is a very important list to consider. And when it comes to cycle times, and when we talk about mold steel selection and temperature, etc., high thermal conductivity is very important to really speed up the cooling phase. Let's take a look.
How do mold designers choose their steels? There are numerous factors that should be considered for the individual components. Here are some questions that mold designers need to answer for optimal mold steel selection. Is the mold designed for a prototype, a small series production, or a full production mold? How many production cycles will a mold be used for? What type of polymer will be injected into the mold? Will the mold be used for a low pressure and unfilled commodity material, or for a high pressure and engineered glass or carbon filled material? Must the mold be corrosion resistant because of certain polymer materials or the molding environment?
Of course, there are many more reasons for determining what mold steel is correct. Again, these are just a few. And remember, when we go through these lessons, this is a training lesson, so there will be a lot more things that are necessary to really determine the ultimate mold steel for each application. But for example, corrosion resistance. Yeah, we have materials that are not so much used anymore in this industry, but like PVC, for example, it's highly corrosive when we process this material under high temperatures, and that's when we really need corrosive resistant steels for the mold. But for most parts, the medical industry is always like to go with stainless steel as well. So let's keep going.
This table provides some mold steel options for different polymer materials, injection pressures, and production cycles. If the mold does not require corrosion or wear resistance, has low expected injection pressures and low production numbers, an aluminum P20 or 420 stainless steel would be some options. For highly abrasive polymers, molded under high pressure, H13 or D2 materials would be good choices for the core and cavity components, with a 420 stainless steel for the mold base.
As always, it's all about the cost economics of using mold steel. Some of them are more expensive, as you know, and more harder to machine and more difficult to treat. For example, beryllium copper, or many of you maybe know Mold Max HH, high strength alloys. Those are good for certain applications where we need a high thermal conductivity, but they're more expensive. So we will see later in this lesson an example. Okay.
Understanding material mechanical properties is helpful in evaluating mold steel options. For example, properly sizing mold components for the tool assembly will depend on different thermal expansion coefficients of the different mold steel materials. Tensile strength is also an important aspect in mold steel selection. For example, aluminum and copper alloys would need to be evaluated for component fatigue and compressive stress requirements to ensure proper mold functionality.
And just think about it. If you use different mold steels and trying to achieve a common temperature inside the mold, a beryllium copper expands and contracts based on temperature differently than a stainless steel or an H13. So when a mold is designed, each of the components you are used have to be sized correctly to the mold temperature range you would like to use. Okay, so the fit and function in the tool is guaranteed.
The cooling phase of the molding cycle is the longest and therefore the most important time period of the molding cycle. Decreasing the cooling time of a polymer inside the mold improves overall productivity. Therefore, mold designers should not only be optimizing cooling line layouts based on part geometries, but also have the ability to evaluate various tool steels to improve heat removal.
Now, why did I put packing as part of the thermal phase? Well, remember in the molding cycle, when the material is heated in the machine barrel, it's hot, it's injected through the nozzle and nozzle tip into the mold, and as soon as the material hits the mold steel, the cooling phase begins. So part of the filling phase is already cooling the material, but mainly when we talk about cooling phase, the phase in the packing phase and the cooling phase, or what we also call remain cooling time. So packing time and remain cooling time is the cooling phase. So during packing, the material cools as well, of course. And so we need to take care of understanding the packing phase and cooling phase as being the overall driver of the cycle time, and therefore we need to pay attention to these two phases during the processing.
It is a general industry-wide practice to use aluminum for low production or prototype tooling because of cost. But aluminum also has a high thermal conductivity and will therefore carry heat energy quickly out of the tool.
Now think about it. You produce, you have a new part design. You have to bring to market. You are making prototypes. The prototypes are in an aluminum tool, and everything goes well. And say, okay, now let's start up production. And you get into a production tool environment and have used then 420 stainless or H13 here, and all of a sudden the cycle time and product quality is different. Remember, aluminum has a high thermal conductivity. A cycle time could definitely change rather quickly. Surface appearance of parts. So remember when you start a new project and you know you're building a prototype tool out of aluminum, it may be different than the production tool just because you're using a different tool still.
Other factors for mold steel selection are the hardening procedure and surface treatment. Diamond chrome plating, hard chrome plating, and nickel boron nitriding are just a few examples of surface treatments that can be used to alter steel surfaces.
And each one of them has advantages, disadvantages. There's so many different treatments available. It really depends on the material, the plastic material you're using and what you're really trying to do. So your tool maker is a good source for additional information, as you can imagine. Okay.
In this lesson, we will evaluate the temperature behavior inside a collet mold. Our example is a 4-cavity mold with a side edge gate cold runner system. The part is molded in a PA66 material with mid-range melt and mold temperatures and a cavity fill time set to 1.5 seconds.
Remember, this is training, and therefore nobody would really design a runner system like this, not necessarily. So keep that in mind when you look at the results. Again, just for training purposes.
Let's begin with the filling behavior for this mold. The fill pattern indicates slight flow hesitations in the thinner outer walls. Polymer flows along the path of least resistance, and because the center round circular feature has a thicker wall, it is the preferred flow path. The hesitation in this example is not severe, and no weld lines or entrapments are evident. Here you can see the overall injection pressure requirements and melt thermal behavior during filling. The injection pressure to fill the mold is 28.4 megapascals, which is well within a molding machine's capabilities. The flow front temperature animation shows the temperature of the polymer as it flows inside the mold cavity and lets us evaluate the temperature differential. If the temperature differential is too large, there may be a hesitation effect that would cause flow-induced marks. In this example, the flow front temperature indicated a relatively narrow range of about 30 degrees Celsius. The differentials here are caused by the flow hesitation in the small connecting ribs between the center ring and outer feature.
That's right here. You may saw this during the fill process here. These thinner ribs causing a hesitation, therefore the pressure, the temperature drops in these areas quite significantly, and you get maybe a surface defect right here. So anything that you can do prior to mold build is very important. You need to optimize the part design before you go to tooling. Otherwise, you cannot fix it afterwards easily anymore. Okay.
Now let's look at the cooling behavior of the part inside the mold. This animation shows the melt core behavior of the part and cold runner system during the packing and cooling phase. The center thicker round features cool last and therefore carry the high heat to the center core. The heat from the polymer must be removed by the mold components.
Okay, so again, this is just showing you how the part cools. All the translucent areas are frozen at the same time increment, but you see this very thick wall here in the center that carries a lot of heat. So if we know this, that we have areas in the tool that carry a lot of heat, that means the mold maker needs to know this to take care of these hot areas with potentially some additional waterline layout, some larger sizes, or some special steel. Okay, let's take a look how to do this.
Our next set of examples has slightly different mold designs. The first set of simulations use the part and runner assembly and core, cavity, and waterline layout on screen. The two-line water circuit is on the fixed side of the mold. The movable mold half has a center insert to form the center ID of the part and a ring water circuit around the insert. The 420 stainless steel mold material data used for these simulations is shown on screen.
Again, simple training for mold steel. What we have here again is two water lines on A and B side, water jacket around an insert that forms the inside of this inner core. Okay, that's our starting point when we evaluate mold steel selections for this particular part. Again, right now everything is out of 420. Okay, let's see what happens.
This animation shows the tool temperature development over 4 molding cycles. As you learned in previous lessons, a mold undergoes a cyclic temperature swing during the molding process, and it is important to maintain uniform temperature behavior from cycle to cycle. The mold temperature set point is 85 degrees Celsius. The simulation shows the mold cut through the center, so you can see the polymer enter the cavity and watch how the heat is transferred from the polymer to the mold. At the end of the cooling phase, some areas inside the runner system are above the material freeze temperature of 220 degrees Celsius. The maximum temperature reached is 249.6 degrees Celsius.
So, and that happens to every mold. Every mold goes through a cyclic temperature cycle. What that means is when hot material comes in, the temperature around these cores or where the runner touches the steel gets hot. During the cooling phase, the temperature drops. So it's a cyclic temperature curve during the cycle. And understanding this temperature curve or this cyclic behavior from high temperature, then low temperature, then mold open, then high temperature, then low temperature. Knowing this temperature range is important because it tells you something about how reactive your mold cooling is. How well is this mold designed in regards to placing water lines and addressing these temperature challenges in the mold. Right in here, you can really see now in a cross section, this is the ring circuit. Yeah, so the ring circuit of the water goes from here around the insert and back to the next insert. And when we watched this movie, we saw the material coming in and these cores getting pretty hot.
This animation shows the tool temperature development without the polymer material. Notice that the tool steel temperature rises to 141.8 degrees Celsius near the gate, and that the highest temperature is at the top of the thin steel section. There is a temperature variation of about 56 degrees Celsius, which is a significant range that could cause cooling-related dimensional and surface appearance challenges.
We saw this during this animation that when the material comes in, the steel really shows a cyclic temperature behavior, and the highest temperature was right here at these corners of these steel components here. This is one core, remember, one core, but there's a cutout here. Right there, right there, right there, right there. 4 cutouts. So the temperature gets the hottest right at these very upper core edges. That's where the temperature is the hottest. And the movie showed this very nicely.
The next series of simulations will incorporate a high-hardened and high-conductive beryllium copper alloy for the entire movable mold base. The core steel is now S7. Let's look at the temperature behavior with this change.
Again, this is training. Remember, nobody would build an entire mold base out of beryllium copper. Way too expensive. Yeah, but for training purposes, this is a very interesting to see. So the base here, and only on the B side, is beryllium copper, and this insert here that forms the internal is now S7. Okay, let's start this again.
The polymer temperature behavior during the filling and cooling phase for the second example has a similar temperature range of 85 to 293 degrees Celsius. The temperature distribution at the end of cooling indicates a maximum temperature of 247.3 degrees inside the runner system.
Yeah, much different it looks like, yeah? The temperature behavior? Or is it?
Here you can see the temperature development without the polymer material. This 4-cycle temperature animation shows a dramatic difference in the mold temperature distribution. The mold temperature range is now only 20.8 degrees Celsius. Here you can see the mold temperature cross sections for the examples at the end of the cooling time. The colors clearly indicate the difference in the mold temperature distribution. By changing the mold base material to beryllium copper, the temperature variation was minimized. The S7 center core shows the highest temperature near the top center and lowest temperature near the ring waterline. The mold thermal analysis indicates that the S7 core cannot remove heat from the center core to the waterlines very quickly due to its lower thermal conductivity. This mold temperature evaluation indicates that using a beryllium copper mold steel will result in a more manageable mold temperature distribution. But the cost for this high thermally conductive steel is also much higher, so may not be a practical solution. Let's look at some other options.
So just let's review this very quickly here. So what we see in the two different varieties. Remember, this was all stainless steel, and this was the mold base only was beryllium copper and these cores were S7. So now S7, as you can tell, has a lower thermal conductivity. And if S7 has a lower thermal conductivity, what will actually happen is you get a very nice temperature distribution through this beryllium copper mold plate, but here's hot and here's cold. What happens? Well, this S7 is now almost like a heat trap. The polymer gives up the heat to the core, but it cannot travel to the waterline so fast that it maintains the heat up here. Amazing. Let's keep going.
In this next example, the movable mold half-core insert and waterline setup have been modified. The center core is now comprised of the entire movable half-core. The ring water circuit is moved closer to the parting line, and an additional baffle circuit is added to the center core section.
Yeah, so different setup now. The tool designers have decided, you know what? I don't think this really worked very well, what we have designed so far. So what they've done is they extended the insert and kept the water jacket around the top and added a baffle circuit here. And okay, but let's go back and keep this at stainless steel because it's a lot cheaper than making the whole base out of beryllium copper.
The mold steel for this example is 420 stainless steel for all the components. Here you can see the outer core features have a higher temperature. The maximum temperature of 137.2 degrees Celsius is in the core feature on the gate side of the mold. Due to the center baffle circuit, the center core has an acceptable temperature distribution.
Aha, so here, this helped a great deal to optimize the temperature of this insert now. It all looks like blue. That means relatively uniform temperature.
Comparing this third example with the first, here you can see the temperature distribution for the two designs. As a reminder, the mold steel for all the components is 420 stainless steel. The hottest portion of the mold is near the gate in the thinner outer core section. Moving the ring water circuit closer to the outer core had a minimal impact on temperature. But the addition of the center baffle circuit reduced the core temperature to an acceptable and controllable level.
Yeah, we could definitely see that in our initial design, making everything out of 420, there was a little bit of higher temperature right in the center of the core, which is now gone because we added the baffle. So cooling design matters. Cooling design really matters.
The final example uses a high-hardened and high-conductive beryllium copper alloy for the center core and a 420 stainless steel mold base. Let's look at the mold temperature behavior for this final mold design. The cycle temperature analysis shows an overall temperature swing from 82.9 at the outer perimeter of the mold to about 157.8 degrees Celsius. When the mold opens, the inside high temperature is 100 degrees Celsius, near the center at the edges to the cold runner system and not in the core region. The highest temperature in the center core is near the gate at about 96 degrees Celsius.
What a different picture, huh? That looks a lot more uniform than what we had before. So a stainless steel base, a higher thermal conductive insert, really create a lot more uniform temperature in this entire section here, in the tool.
Here are the four design and mold steel temperature distribution results. When the ring water circuit was moved closer to the outer core section and the center baffle circuit was added, the results indicate the most uniform temperature distribution. But more importantly, by using a highly conductive beryllium copper alloy, the temperature inside the center core is more uniform. For minimizing mold tool steel cost, a combination of 420 stainless steel for the mold base and a high hardened beryllium copper alloy for the center core could be used.
Yeah, so this is basically the final review here. It is a lot common to use 420 stainless for the mold base, just to be corrosive resistant. And in some applications you can use, of course, other steel. You can use P20 S7. That's not uncommon that you have a mold base out of those two materials as well. And again, this is just an example to show you that it is important to verify what's your goal and objectives with this tool design. When we just look at the sec number 3 and number 4 and compare those, that's the same mold design, the same cooling line layout. The only difference is that the top here, number 3, example number 3, it's all 420. And example number 4, the base is 420, and this core that forms the inside of the part is beryllium copper or Moldmax H or some similar material that has a high thermal conductivity. But look at the temperatures. With all stainless, the highest temperatures are 137 or 279 Fahrenheit. With the exchange of the beryllium copper or the high thermal conductive core, it dropped to 212. Wow, what a difference. Of course, this will impact not only the part quality, but also the cycle time and therefore profits. So it is very important to calculate, okay, I spend more money on these cores because they're highly thermal conductive, but I maybe make up this money if I have to run millions of shots or hundred thousands of shots and save it on cycle time. So what I'm trying to tell you here is, number one, when you look at saving and optimizing quality, trying to optimize the quality and save cycle time, it starts with the part design. The part design needs to be optimized to cool uniformly. Then you give it to the mold designer who needs to mimic this behavior by laying out the water lines and tool steel selection correctly. And only then you have a mold that will function properly and gives you a low cycle time and high quality and therefore greater profits. Okay, that is very, very important.
This concludes Section 4, Mold Design, Cooling, Lesson 6, Mold Steel Selection. In this lesson you learn the most common mold steel materials and what attributes they should possess, the best mold steel options for different polymer materials, injection pressures, and production cycles, temperature distribution behavior for molds with different mold steels and mold components. Injection molding is a process of heat exchange. Managing this process is critical to part quality and minimizing production costs. Performing mold thermal analyses on new tooling allows mold designers to evaluate potential design and process challenges prior to mold building and production. Depending on polymer materials, injection pressures, and production cycles, designers can determine what mold steels to use that will reduce production costs and improve molded part quality.
Okay, I have one more thing I would like to show you, so stay tuned for just a few more minutes. And let me get out of our online learning system here. Again, you can check this out obviously on the cruisetraining.com. There's where all these lessons are hosted, where all of our really cool 3D animations are coming from. We have our own animation people that do all that. So anyway, I wanted to show you one more application that I'm currently working on, which is kind of interesting. And again, this is a training sample. Actually, this mold exists, but it's used by our partner in Germany, Contura GmbH, and I'm going to show you here a few aspects of this. So basically, this is the part, and the system needed to be designed such that, well, let's put the water lines in. I'm going to show you these water lines that are part of this conformal cooling setup here. It's very interesting to see this for you. See, these are the water lines. Take a look at this. Oh my Lord. Yeah, conformal cooling, everything conforms to the part geometry, and that makes it really interesting how this will perform. Let me show you just a result here, which we call streamlining. Streamlining is basically showing you how the water flows through each of these channels. This is what we can call conforming cooling water CFD analysis, where we really take the water put it in and see how it swirls around and goes through each of these individual channels to see if we have hot spots, dead spots, if you can see the pressure drop through the system, what the water temperatures are in the individual systems. Yeah, but you know what? This is only one part of it. Another part is that let me take out the water lines and show you what else they put into the system. Let me get out of here. Okay, we go back to the model. Here's the B side. And of course, these water channels are marked in. But what you don't see is all of these little markers in here. I want to show you those. See these blue markers on the screen? Those blue markers are pure copper inserts. They have been put into this conformal cooling mold cavity to further enhance the withdrawal of the water. Yeah, some of them, as you can tell, they touch the water, and the water is cooling the system, cooling these corners inside of the part very quickly. And of course, this is not only on the movable side, but this is also on the fixed side. Yeah, the fixed side has also all of these copper inserts surrounding the part, and even around the hot drop system, we have pure copper inserts that cool the hot sprue area near the gate. So this is what I call conformal cooling. What I showed you in the lesson was a simplification of what conformal cooling can be. This is the ultimate in technology nowadays, that you can really import not only conformal water lines, but adding pure copper inserts in critical areas to create what I call a super duper conformal cooling setup. Okay, just I thought this was important and wanted to show you this because it was kind of interesting to see that. Okay, so now let's stop this and finish up. So again, what our intention is with our system is really trying to teach part designers, mold designers, and processors to really talk to each other more often and really discuss things. The circle of knowledge system as well as is alive and well. And if you need to contact me, if you have any questions, I saw we have a few questions in. I'm going to send those out through you, Jeremy, on an email. But if you need to contact me, here's my contact information. Do not hesitate to send me an email or call. Not a problem. I'll be happy to help you along. And again, thank you very much for participating. The next webinar is scheduled for the later fall. So just check out the website on the webinar link and you will find where it is. So have a good day and thank you for participating.